nature of distances between objects, and how no matter how close two things are, it seems that they can always be brought a little bit closer together without touching. Fond of math as you are, you want to capture this paradoxical feeling with numbers, so you imagine placing the two objects on the number line, the first at 0, the second at 1. Then, you march the first object towards the second, such that with each step, the distance between them is cut in half. You keep track of the numbers this object touches during its march, writing down 1/2 plus a fourth, 1/2 plus a fourth plus an eighth, and so on. That is, each number is naturally written as a slightly longer sum with one more power of 2 in it. As such, you're tempted to say that if these numbers approach anything, we should be able to write this thing down as a sum that contains the reciprocal of every power of 2. On the other hand, we can see geometrically that these numbers approach 1. So what you want to say is that 1 and some kind of infinite sum are the same thing. If your education was too formal, you'd write this statement off as ridiculous. Clearly, you can't add infinitely many things. No human, computer, or physical thing ever could perform such a task. If, however, you approach math with a healthy irreverence, you'll stand brave in the face of ridiculousness and try to make sense out of this nonsense that you wrote down, since it kind of feels like nature gave it to you. So how exactly do you, dear mathematician, go about defining infinite sums? Well practiced in math that you are, you know that finding the right definitions is less about generating new thoughts than it is about dissecting old thoughts, so you go back to how you came across this fuzzy discovery. At no point did you actually perform infinitely many operations. You had a list of numbers, a list that could keep going forever if you had the time, and each number came from a perfectly reasonable finite sum. You noticed that the numbers in this list approach 1, but what do you mean by approach? It's not just that the distance between each number and 1 is smaller, over there, because for that matter, the distance between each number and 2 also gets smaller. After thinking about it, you realize what makes 1 special is that your numbers can get arbitrarily close to 1, which is to say, no matter how small your desired distance, 1/100th, 1/1,000,000th, or 1 over the largest number you could write down, if you go down your list long enough, the numbers will eventually fall within that tiny distance of 1. Retrospectively, this might seem like the clear way to solidify what you mean by approach, but as a first-time endeavor, it's actually incredibly clever. Now you pull out your pen and scribble down the definition for what it means for an infinite sum to equal some number, say x. It means that when you generate a list of numbers by cutting off your sum at finite points, the numbers in this list approach x in the sense that no matter how small the distance you choose, at some point down the list, all the numbers start falling within that distance of x. In doing this, you just invented some math. But it never felt like you were pulling things out of thin air. You were just trying to justify what it was that the universe gave you in the first place. You might wonder if you can find other, more general truths about these infinite sums that you just invented. To do so, you look for where you made any arbitrary decisions. For instance, when you were shrinking the distance between your objects, cutting the interval into pieces of size 1/2, 1/4, etc., you could have chosen a proportion other than 1/2. You could have instead cut your interval into pieces of size 9/10 and 1/10, and then cut that rightmost piece into the same proportions, giving you smaller pieces of size 9/100 and 1/100. Then cut that tiny piece of size 1/100 similarly. Continuing on and on, you'd see that 9/10 plus 9/100 plus 9/1000, on and on up to infinity, equals 1. A fact more popularly written as 0.9 repeating equals 1. To all of your friends who insist that this doesn't equal 1 and it just approaches it, you can now just smile, because you know that with infinite sums, to approach and to equal mean the same thing. To be general about it, let's say that you cut your interval into pieces of size p and 1 minus p, where p represents any number between 0 and 1. Cutting the piece of size p in similar proportions, we now get pieces of size p times 1 minus p and p squared. Continuing in this fashion, always cutting up the rightmost piece into those same proportions, you'll find that 1 minus p plus p times 1 minus p plus p squared times 1 minus p, on and on, always adding p to the next power times 1 minus p, equals 1. dividing both sides by 1 minus p, we get this nice formula. In this formula, the universe has offered a weird form of nonsense. Even though the way that you discovered it only makes sense for values of p between 0 and 1, the right-hand side still makes sense when you replace p with any other number, except maybe for 1. For instance, plugging in -1, the equation reads 1 minus 1 plus 1 minus 1, on and on forever, alternating between the two, equals 1/2, which feels both pretty silly and kind of like the only thing that it could be. Plugging in 2, the equation reads 1 plus 2 plus 4 plus 8, on and on to infinity, equals -1, something which doesn't even seem reasonable.
We're not.
On the one hand, rigor would dictate that you ignore these, since the definition of infinite sums doesn't apply in these cases.
Definitely.
The list of numbers that you generate by cutting off the sum at finite points doesn't approach anything.
Again, inventing this math is over. That is kind of how that is.
But you're a mathematician, not a robot, so you don't let the fact that something is nonsensical stop you. I will leave this sum for another day, so that we can jump directly into this monster.